Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. We've done quite a few videos now when it comes to derivatives, so we know how to calculate derivatives. What I want to look at in this video are how some of those derivative formulas are derived. And you know, some of these formulas we've been taking at an advantage so far. We've taken them literally at an advantage, like we've unknowingly been doing procedures without understanding how some of those formulas were derived, and it's okay. Sometimes it's better just to learn the technique before you learn how the technique was developed. And sometimes that's a good way, because when you're learning how the technique was developed, you already have the understanding of how the technique works. One of the formulas that we want to look at, we'll look at several, but one we want to look at, and keep in mind many of these also depend on having a knowledge on the laws of limits. There are a variety of laws of limits, so some of these derivations of these differentiation formulas build upon those techniques which are presented in the laws of limits. So the one which we want to look at first is the one to do with the constant multiple rule. You know, if you look at any derivative which has a constant, you can push out the constant and do the derivative and bring back the constant. And we're looking at something which would be in this form. If you're looking at a derivative of a function, and that function had some sort of a constant, you see C for a constant, something which would look like 2x squared. You know, here's a variable part, here's a constant. When you normally do the derivative of this, you basically end up with something which looks like this as an answer. Think about it. When you do the derivative of this, you have 2x, and you bring this 2 along with it, you multiply it, and you end up having 4x, right? All along you've been doing simple derivatives or even hard derivatives, but you never looked at things in terms of how they were derived. So this is what we're looking at in this video. So you can look at this type of a representation in this form, where the constant is pushed outside, and then you're doing the derivative of just the variable part. So you can verbalize this. The derivative of a constant times a function is the same as taking the constant and multiplying it by the derivative of that function, which is right here, constant multiplied by the derivative of that function. What we want to look at is how this formula is derived, the procedural formula, how it derives, and everything derives over here based on the basic definition of a derivative. And you know what the basic definition of a derivative, which builds on the concept of the secant lines. You've seen this right here. If f of x represents some sort of function, the derivative of this function is represented by the basic definition of a derivative, f of x plus h minus f of x divided by h. Everything kind of stems from this application of this formula. So let's look at that for this representation over here, how it comes about. So let's look at it, and then we'll do the derivation over here. The derivation will go in this way. If supposedly g of x represents a function which looked something like this. If g of x is something like c times f of x, a constant, if you can represent this in terms of g, then what we're really looking at is the derivative of g of x, which would of course be limit as h approaches 0, you're doing g of x plus h minus g of x over h. But what exactly was g of x? It was really c of f of x. So you can do all of that in terms of substitution with regards to this right over here. And how it would play out is this. You would have limit h approaching to 0, you'll have c times f of x plus h minus c times f of x divided by h. Isolate the c, you'll have limit h approaching 0, you've isolated this c, you'll have f of x plus h minus f of x over h. Using the law of limits, you can even bring the c right out over here. So you're looking at something which looks like c times the limit h approaching 0. You have something which looks like f of x plus h minus f of x over h. What do we end up having over here? The basic definition of a derivative with a c attached to it. So you're looking at something which looks just like this right over here. And that's how you can show that something which looks like this is equal to that a function multiplied by a constant is the same thing, and doing the derivative of that is the same thing as taking the constant and multiplying it by the derivative of that function. That is, the constant was pushed aside and then brought back in at the end, and we've shown it to you over here. So this right here is going to be the start of this video, and we'll be looking at various other formulas, but in this type of a manner, and then you'll in this video learn how some of the things you've been taking for granted or as an advantage to your techniques you'll be learning how some of these techniques were developed. You know, I've formerly presented videos on the chain rule, the product rule, and the quotient rule. Those are 3 specific rules, and those 3 specific rules developed and used formulas that were inherent to the types of questions I presented in those videos, where you had a product of functions or a quotient of functions, or where the chain rule was required. And you were inherently using a technique, but we never looked at the derivation of those techniques, and that's what the purpose of this video is. Something which I not formally verbalized was a sum rule, and I've shown you questions which employed the sum rule, even though I did not formally devote a video to it. Similarly, there was questions which developed and required the difference rule, and we'll be looking at those here. If I had a question which looked something like this, derivative, and I said find the derivative of this polynomial 2x squared minus root x plus root x. Let's make this a plus because we're talking about sum. You know, this right here would require something called a sum rule, because you could distribute the derivative across, and you could look at these individually as monomials and easily do this. So what are we talking about here in terms of the sum rule? It's basically saying that the derivative of a sum of function is equal to the individual sum of the derivatives. That's what the rule is saying. But how is this rule formally developed or derived is what we're going to look at now. You have something which looks like this. If f of x, capital F of x, represents the sum of 2 functions, f of x and g of x, how can we show that the derivative of this is equal to the sum of the individual derivatives? And what is the derivation formula? Well, I'm going to present that to you. The formula presents in the following manner. If this right here represents the sum of 2 individual functions, what you're really doing is looking for this. Remember, this prime means you're doing the derivative of that function. This right here represents you're doing the derivative of that. And then you run it through its formula, and you know the formula is limit as h approaches 0. You have f of x plus h minus f of x over h. What you have to do is adapt this top part right here to this part right here, and suddenly everything becomes something like this. F of x plus h plus g of x plus h. This right here is this f of x plus h. This capital F of x plus h has been opened up into this part, because capital F of x is the sum of these two minus the f of x and the g of x part. And you know that's not going to be too hard. You'll have to parenthesize over here f of x plus g of x, because we're looking here at the sum rule, the sum of functions, the derivative of the sum of functions over h. What you have to do is separate things over here. Open and separate. Limit h approaching 0, you have f of x plus h. I'm going to bring this minus f of x with it, because I'm bringing like terms together, like terms. Minus g of x all over h. Separate everything using the law of limits. Remember, you have to use the law of limits over here. Limit h approaching 0, you have f of x plus h minus f of x over h, plus limit h approaching 0, you have g of x plus h minus g of x over h. Now you have individual limits. This looks very much like the formula which you would do for the derivative of the f function. And this, remember this prime, let's make the prime clear. And this looks very much like the formula of a derivative of a g function, right? G prime x. And that's exactly what we've done over here. We've shown you this, that the derivative of the sum of 2 functions is equal to the sum of their derivatives. So we've shown that by using this procedure, you have exactly this. That if something were to look like this, f of x plus g of x, and you're doing the derivative of this right here, what you end up getting is this f prime x plus g prime x, which means the sum of their individual derivatives. And the formula is proved using the manner over here, and this right here is the sum rule of derivatives. The difference rule is very similar to the sum rule, except here when you're looking at a function, remember everything here depends on how you're notating it. If f of x represents the difference of 2 functions, and you were to do the derivative of f of x, capital F of x, you could easily do individually the derivatives and you'd still be right. You see, you could distribute the derivative across the 2 functions. So how do you verbalize this? You can verbalize this that the derivative of the difference of 2 functions is the same as taking the difference of their derivatives. I'll say that again. The derivative of the difference of 2 functions is the same thing as the difference of their derivatives. And You can prove it using similar approach as we did previously. If your main function is capital F of x and you're really finding the derivative of that, which represents the difference of two functions, well, you can do it exactly as we did before and approach it in the same way. You have to just maintain proper terminology over here. And remember, everything here stems from the basic definition of derivative, which involves the secant lines. You know all of that. And what you have to do is now substitute this part for the capital F part, because the capital F represents the difference. And what you end up having is this limit h approaching 0. We'll lay it out for you over here. You'll have f of x plus h minus g of x plus h. That's just this part right here treated. Then we have this minus part, and then we'll do minus f of x and minus g of x all over h. You can open the parentheses out. I'll do that. Limit h approaching 0. I'll have f of x plus h, and I'll combine them. When I open up this parentheses, I get a minus f of x, which I'll combine with the f component with its own h. And then I have this minus over here, but I'll have a plus here with the g of x, because this minus will multiply with this minus, you'll get a plus. What I want to do is keep a minus here because we're looking at a minus or a difference rule over here. And then I'll lightly add this g of x plus h, and then I'll have over here a minus g of x, and then over h. So it doesn't take much more from here than to bring in the law of the limits, and there's nothing wrong over here. Think about it. If you do this minus multiply this g of x plus h, you'll have a minus g of x plus h, which is what we're seeing right over here. If you multiply this minus with this minus, you'll have a plus g of x, which is what you would have gone from right over here. This minus multiplying with this minus would have retained, we would have made it positive. This minus here would have retained the minus. So sign wise we are good. All we have to do is now separate everything under their limits using the law of limits. Limit h approaching 0, you have f of x plus h minus f of x divided by h. This right here represents the derivative of f, this f function right over here. Then you have this minus sign, and you have this new limit. Remember the law of limits, g of x plus h minus g of x over h. And when you compute all of this using terminology and what this expression stands for, this expression here stands for this right here, the derivative of the f function, right, or the lowercase f function. This right here stands for the derivative of the lowercase g function. So we've shown you this. If you're doing the derivative of this capital F of x, then you're looking at the individual difference of their derivatives, or you're looking at this f prime of x minus g prime of x would equal the derivative of this capital F of x, which was originally the difference of these two functions. And you have it right here laid out to you. So this right here is a difference rule which has been proved, and you can say it has been derived for you. You know application wise how this looks like. It's very easy. I won't go through it. You think about any polynomial which has minus signs, and you can break that polynomial into their individual derivatives and then compute everything towards a unifying answer at the end, and you've seen all of that. We'll look at the product rule and the quotient rule for the remainder of this video and how those two rules are derived, and that'll be it for this video. So let's look at the product rule, a rule that we've used so frequently, but we've never really understood or determined how the rule came about. We've intuitively used it, but we've never really studied as to why the rule works the way it does. We know exactly what the rule is. So we know when you have a specific function which is made up of a product of two functions, this capital F of x is equal to f of x g of x, and we know this right here is a product rule template. The product rule template, when you verbalize it, is the g function multiplied by the derivative of the f function, and adding to that the f function multiplied by the derivative of the g function. What we want to know and understand is how is this formula derived, and this is how it is. If this right here represents the product of two functions, what you are really doing is looking at the derivative of this, aren't you, right? So the f prime x is equal to what we'll show from here onwards, the derivative of this, which is a product of two functions, and I'm going to show it to you right over here. It will really be f of x plus h. It's going to follow this scheme over here, minus f of x, just the basic formula of a derivative, except we're going to be using the proper terminology and we'll bring it in. We know this capital F of x is a function made of two separate functions, f of x and g of x, and we have to bring that into this picture. And how will it happen? I'll show it to you. Limit h approaching 0, you'll have f of x plus h multiplying by g of x plus h, right? F of x plus h multiplying by g of x plus h minus this part right here, which will be minus f of x and g of x all over h. Remember, in all of these rules, derivations, we're using the basic definition of a derivative to show how the rules are established or derived, and that's exactly how it is. To do proper separation, isolation over here, we have to bring a specific factor. You know, using the laws of equality or neutrality or balance, if you're adding something, you must remove it away somewhere in the process, so what you started with stays exactly what it is. You have not added anything extra, nor have you taken extra. So if I'm going to bring in a factor to help me isolate and deal with all of this, then I must remove that factor. The factor that I'm going to bring for this derivation formula is this. It's going to be this. I'm going to write it out right here. F of x plus h and g of x. This is a factor that's going to help me deal with this. Let's call it a mess. It'll help me deal with that mess. I'm going to add it in here and I'm going to minus it in here only to help me isolate and separate things properly. And let's do that. Limit h approaches 0. We have f of x plus h and g of x plus h. Now let's add in that factor plus f of x plus h and g of x, and then let's also minus it. You'll see the purpose of all of this momentarily. You see, I've added the same factor, then I've minus the same factor, so I'm maintaining the balance, the neutral aspect, I'm maintaining it. Minus f of x, g of x, all over h. Now we have to find some common terms over here. That's the whole purpose of bringing in that factor here, was so I can do isolating and dividing and simplifying and getting to this product rule template I have. So now that I've done the incorporation of the factors, I need to somehow find common terms, and I'm going to look at something over here. I'm going to look at this thing right here with this here. Then I'm going to look at this part right here with this part right here, all with their denominator. So let's do that. Limit h approaches 0, and you'll see why the factor came in. If you're adding and minusing it simply to help you deal with this part right over here. If you look at these parts here under this flat bracket, you have f of x plus h and you have f of x plus h. You can isolate that. You'll have f of x plus h. When you isolate that, you have this g of x plus h right here, g of x plus h, and then you have this minus gx, g of x. Remember, you can always hold on to this image and look at it carefully over its denominator. Then I have these parts here under these triangular brackets, and let's look at that. I have a f of x plus h and g of x. Here I have a minus f of x and g of x. What are the things I can isolate right here? I can isolate the g of x, and then I will do that across this positive sign. I have a g of x. From this g of x and this g of x right here, you isolate this f of x plus h, because that remains, minus this f of x. Remember, you can always hold on to all of this in terms of your image and see how things are playing out. I'm seeing a definition here of a derivative coming here. I'm seeing a definition here of a derivative coming here. I have a specific function here, f, and I have a specific function here, g, coming into play. I'm going to separate everything across their individual limits using the law of limits. Limit as h approaches 0. I have a f of x plus h, limit as h approaches 0, and remember, each of these parts right here are in a times relationship. I have this g of x plus h minus g of x all over h. Then I have this positive sign. Then I have this limit h approaching 0. I have g of x. Then let's bring in this part right here under its own limit. Limit h approaches 0. And this is how these formulas or these rules are derived. F of x plus h minus f of x divided by h. Now it's not much at all here to take everything to completion. This limit h approaches 0 of f of x plus h, if you were to plug 0 here in place of h, what would you end up with? You would end up with just f of x. Remember, everything here, capital, everything, lowercase, all of that matters because notation and terminology here matters. If you look at this part right over here, this looks like here the basic definition of a derivative for a g function. But the definition of the derivative of the g function, so let's bring in this prime, because you know the prime here represents the derivative of the g of x. If I were to say find the derivative of g of x, this right here would give you the derivative of g of x, which you can represent right here as I have in terms of the representation, the notation, and the terminology. Plus This right here looks like the g of x just alone. You can't do anything with it. Limit as h approaches 0. This part right here represents the derivative of a f of x function. F of x, the derivative of that is represented right here in terms of its terminology and presentation. So look what I have over here. I basically have the template here for the product rule. The f function multiplied by the derivative of the g function, add to that the g function multiplied by the derivative of the f function, or order does not matter, across the positive sign and flip everything around. The g function multiplied by the derivative of the f function plus the f function multiplied by the derivative of the g function. In here, under this underlined part, or above this underlined part, I have my product rule, and it's been derived for you. It could have been a little tricky, or it could have been a little messy, or maybe a little confusing, but you have the image over here to look at, and you can look at it and see how it's been derived. The most difficult part of this derivation is this right here, bringing in this factor right over here to help you solve this down, because you needed to add it in here and minus it in here to do the separation, but you didn't do any net gain or net loss, because what you added in you minused out, so you maintain the balance. We'll look at the quotient rule next. It's a similar procedure, and that'll be it from this video. So we end the video with this quotient rule, and you know the template for the quotient rule, we've talked about it. The derivation of this is not as easy as that for the product rule, but it's not overly complex. Our only challenge here is to fit the procedure here in the space we have. You know very quickly for any function, and look, you have to be careful here with your notation, and you have to maintain the consistency of that. If a function, capital F of x, is a rational function, and you know the capitals and the lower cases, all of that matters. What would be the basic template of the quotient rule? And you know it. It's a g function multiplied by the derivative of the f function, right? And then you minus the f function multiplied by the derivative of the g function all over the g function squared. So that right there is basically our template for the quotient rule, and you know you can very simply say it in this way, and you have to be careful with the terminology and notation. G f prime, right? G function multiplied by the derivative of the f function minus the f function multiplied by the derivative of the g function over the g function squared. And you know this right here is a quick way of showing it. Very quickly for the product rule I've shown you, you can say this right here is the quotient rule template. The product rule template can be very quickly showed as this way. The g multiplied by the derivative of the f plus the f multiplied by the derivative of the g. And a very important point to remember here, if you're looking at the product of two functions and you're doing their derivative, which is exactly why you're doing the product rule. Remember, the product rule is you're doing the derivative of the product of functions. It's not the same as just distributing this prime across the two. This right here is not it. You know, when you do the product rule, you end up getting this. And likewise, if you're doing the quotient rule or the derivative of a rational function, if you're doing the rational function, the derivative is not simply just distributing this prime across the two by opening up the parentheses. This is not it. It's this right over here. So it's more than just distributing the prime across that by opening the parentheses, because the quotient rule and the product rule brings in some of these extra factors which only arise when you learn the derivation procedure. The derivation for the quotient rule starts in this manner, similar to what we've seen in the previous derivation rules. This capital F of x represents a rational function of this lower f of x and lowercase g of fx. A rational function. Remember, terminology presentation here matter. So if you're finding the derivative of this, you represent it in that way using the basic derivation procedure or the definition function, the basic definition function, and then everything starts from this point onwards over here. Limit h approaching 0. What you have to do is somehow fit this form into what you have over there, and it's not hard. You end up having f of x plus h over g of x plus h. That represents this part right here, f of x plus h. Then minus f of x over g of x. This represents the substitution of this rational function right over here, and everything's all over h. We'll have to try to do everything here with the space limitation that we do have. The way you proceed forward from here is a common denominator of these two items. You have g of x plus h and g of x representing a common denominator. This goes in this g of x times, and it'll multiply with this item here. You'll have f of x plus h times g of x. Then you have this minus sign, This g of x goes in the common denominator g of x plus h times and multiplies with f of x. F of x times g of x plus h. So this is what we have so far. I haven't forgotten about this h, and I can just bring it up right over here. You know, because this is an h over 1. When you flip the denominator, it's going to come right over here and attach to this common denominator we've developed. Just like the product rule, we have to develop a little factor which we added in and we minus from to help isolate, separate, and factor things. There's a factor we have to employ over here so we can deal with this, what we have over here. And the factor is f of x, g of x. G of x, f of x is a factor that we'll add in and subtract from the numerator to help us deal with what we have here. Let's come down over here, limit h approaches 0, and let's add in the factor. We have f of x plus h. I'm right over here and writing what I have. I've written this part. Now let's bring in the factor. We can do minus f of x, g of x, and we can also add it in. Remember, we're maintaining the balance over here, minusing and adding in the factor as we see it. Then let's write the rest. Minus f of x, g of x plus h, all over. We have this h, and then we have g of x plus h, and then g of x. What's the purpose of the factor we have here in the quotient rule and the product rule? It's to help manipulate what we have to come to our desired outcome. We have to see what are the commonalities we can see. I'm just erasing this h and moving it up just so we don't have too much of a clutter. I want to be able to isolate things so that I can separate them out and develop what we need to develop. If I'm looking over here, isolate this with what item would I want to isolate it with? With this right over here. And we'll isolate this with this. By isolating, I mean isolating, factoring, manipulating, so we can help solve what we have. And let's come down over here and let's do our manipulation. When I'm looking at these two items over here under this flat bracket, I have a common here, a commonality of g of x. G of x, common. And it goes right here, f of x plus h minus f of x. Now we're going to do a little bit more of a manipulation. Remember this h we've seen come down over here, this h. Let's bring it back and attach everything to their original functions as you would have using the basic definition of a derivative. Nothing fancy going on over here, but we're just bringing it back up, re-separating it from this common denominator. We attached it earlier to the common denominator, now we're re-separating it back out. And then we have this minus sign right over here, because now I'm looking at this f of x right here, this f of x, which I'm going to isolate with this part right here under the triangular brackets. I'm going to isolate from here the f of x. This f of x is attached to g of x and g of x plus h, which is what I'm exactly going to bring out. G of x plus h minus g of x. I'm going to show you the signs, everything right here momentarily with its own h. And everything is here over a common denominator of g of x plus h times g of x. Now let's look over here again at this second part after the minus sign to make sure we have no problem here with the signs. When I hit this minus f of x with this g of x plus h, I should have a minus f of x g of x plus h, which is what I see here, minus f of x g of x plus h. When I hit this minus f of x with this minus g of x, I should end up having a plus f of x g of x, which is exactly what I have over here. Plus f of x g of x. So there's been no magical tricks over here. Everything is sound, everything is correct so far. The h's have been brought up back to their original items. We have a bit of a space limitation over here, so we can do something here in the bottom right here, then we'll complete it out right over here. We're going to bring everything here with its own limits. Limit as h approaches 0, we have this g of x, which we'll attach to this limit. And then we have this part right here, which looks very good and close to a definition of the f function derivative, the basic definition of the f function derivative. And you know all of that is in a times relationship. This part right here and this part is in a times relationship. Limit as h approaches 0, I have this part right here, f of x plus h minus f of x divided by h. Now I have this minus sign, let's bring the minus sign. We have this part f of x here, let's bring it with its own limit. Limit as h. We have a bit of a space issue over here, but we have to make it work. Limit h approaches 0, we have f of x. And then we have this in times relationship. Limit as h approaches 0. We have all of this, which looks very well like the definition, the basic definition of the g function derivative. Or we have to write it out. G of x plus h minus g of x all over h. We have this large denominator. We have these two items here, g of x plus h and g of x, which have to be separated under their own limits using these. We're separating everything here using their own limits, using the laws of limits. We have limit as h approaches 0, we have g of x plus h, and we're multiplying it by this limit as h approaches 0, we have g of x. I apologize for the space limitation we have over here, but it's readable. We're going to come over here, we're going to finish it up. When I'm looking at this part right here, limit h approaching 0, g of x, and I'll make sure to verbalize everything so we can see what's going on and match it to my words. Limit h approaching 0, g of x becomes just a g. Then we have this part right over here we're looking at right here. Limit as h approaches 0, we have the basic definition of the f function derivative, which we can just write as this, the f function derivative. Then we have this minus sign. Remember, what we're forming here is the template of the quotient rule. We look at this part right here. We just have f function, nothing is happening with it. H approaching 0, f function is just the f function. Then we look at this part here. Limit as h approaching 0, this right here looks like the g function derivative. We come and write it here as a g function derivative. Then we go right here in the denominator. Limit as h approaches 0, g of x plus h. You plug in 0 in place of this h. You just have g of x. That's what you end up getting. G of x, which is just g. You can just abbreviate as g. We have limit h approaching 0, g of x. We just have another g right here. G times g. G times g, you know very well to be g squared. So let's write it out as g squared. And then suddenly we end up having what we have, the template here for the quotient rule, which is what we have wanted all along, the derivation of it. The g function multiplied by the derivative of the f function minus the f function multiplied by the derivative of the g function divided by g function squared. Remember, these primes, again, as I've said, mean the derivative of that function. So again, like the previous rule, the product rule, this one required this specific factor to help complete this derivation procedure. The factor was f of x times g of x. You bring it in right over here, you add it in, you minus it in, but it helps you separate things out. But you see, you use the law of limits at the very end to separate everything out and to manipulate it to your final form. But everything else is here in terms of a relatively clean presentation, but it's clearly laid out for you. You should be able to look at it and understand why this rule is derived the way it is. But a function which looks like this, rational function, you take the derivative of it, it follows this quotient rule, and you know the quotient rule, and you've seen many examples of it. But that's it for this video. We presented the constant multiple rule, we presented the addition rule, which is the sum rule, the difference rule of derivatives, the product rule, and the quotient rule. And those are primarily the main rules that you want to learn in terms of the derivation. The chain rule is not so important in terms of the derivation because it doesn't really have a clear representation in terms of this derivation process as you're seeing, because all the rules I've presented here in terms of the derivation procedures follow a similar format, so I'm presenting them here. But everything is laid out for you. I hope you enjoyed this video. I hope it was beneficial. Thank you for watching. Have a nice day.